Okay. So we'll continue from the morning class where I was discussing about the stress strain behaviors and different factors that could influence the compressive response of your concrete when you do testing. Mainly the loading plateau, the surface interaction between that loading plateau and the concrete surface, and then the load rate that you apply while you test your specimen, and the specimen geometry, and the entrainment. So all these things will influence your testing and thus the compressive strength of your concrete. So when you have to characterize your concrete, you should follow the standards and use the specified given instructions to obtain a uniform result without any significant scatter. So now let's look at the detailed stress strain response of your concrete. So you have your this plot here, the left side that shows the stress strain response of concrete. So initially, in the morning class, I have told your concrete will have very fine bond cracks. So your concrete will have very fine bond cracks at the interface between the steel and between the between the aggregates and hydrated cement paste. So that fine cracks will be there even before you apply any load. Maybe you can say up to 30% of your ultimate strength, your cracks will be, the very fine bond cracks will remain stable and do not grow under stress up to 30%. That is what here it is mentioned, up to 30% you have negligible bond cracks in your concrete. So once the stress level increases beyond 30%, these cracks will slowly grow. So that slow growth of bond cracks connects the cracks, and then your crack length will get increased, and the number of cracks will also increase at that point. And with further increasing load, you can see slow growth of matrix crack plus bond crack. So you will have both these interface cracks as well as the crack growth that connects together, and then that forms a significant long cracks, and that will lead to multiple cracks in the matrix. And then with further increasing, you will tend to see the crack connectivity will be so fast. The fast growth of matrix crack will lead to failure of your concrete specimen. So beyond that point, you can see the concrete cannot take much load. So at this point, beyond this point, you can see your concrete cannot take much load, and you will start looking at a drop in your stress. So this kind of shows the complete stress strain behavior. So you have your ascending branch here, so that corresponds to this region. So where your cracks slowly gets grow with the increasing applied load, and then your cracks are connected, and you can start forming like this long cracks on the concrete surface. So crack propagation will be faster when you reach the ultimate stress. So beyond this point, the strain increment will be faster, and then you will see the material cannot take much load. So you can start looking at a drop at this region after your peak. So that's why typically we call this region as a pre-peak region, and you have this peak region and you have this post-peak region, right? So the post-peak region is important to determine the failure of your material or to characterize the toughness of your material. So I will explain what toughness is in the coming slide. So the pre-peak behavior is important to I determine your elastic modulus value, and in case if you want to know the Poisson's ratio, you can get those things. And after this drop, at one particular point, you will start looking at converging branch. So there, the friction and interlocking between cracked section will be significant, and then the load will be dropped significantly. So the stress is reduced significantly after the converging point. So here is the concept of localization. So this is what I was explaining before, up to this region where the 30% of your ultimate stress. So you will have negligible bond cracks, very fine bond cracks in your matrix, and with increasing load conditions, these cracks will grow slowly, and then it will get connected. And after this peak, you can see this complete cracking at this region. So the crack has propagated so nicely, and those were got connected. And then with further increasing load, your concrete cannot take load. You can start seeing this drop in load after peak. And then until the point the member cannot take load. So when your member fails completely, then your load becomes zero. So here is illustrations to understand how the loading cases affects the concrete stress strain behavior. So as I said, this is the pre-peak region. So when you have your pre-peak region, so where there if you unload, your member can come back to its original condition because that will be in elastic stage. But here in this case, your member has reached its peak, ultimate condition is attained, and then it starts failing it. So you will get the stress strain response at this region will be something like this. In this region, your stress strain response will be like your material is under elastic conditions. So with increasing load, you can reach like this. When you unload it, you can get back to its original position. The same applies for this region also. So here is the illustration of different curves with different compressive strength of concrete. So here the basic idea is that how the strength affects the stress strain performance you have member. So here in this bottom region you can see a curve whose stress is less for about 20 MPa, and the strain is about in the range of 3500 microstrain. As this strength increases, you can see the peak post peak region got reduced. So here your post peak will be somewhere at this point. So here your post peak will be somewhere at this point, but you have after your peak you have this much strain absorption or energy absorption when you use this particular concrete. So as the strength increases, you can see the reduction in post peak response. You can see. So this is the higher strength concrete. So once the peak has reached, the member immediately fails. So the area under the curve is very less for the highest strength concrete comparing to the lower strength concrete. So this is one aspect that we will understand from this curve. Another point is that the initial region. So this is the change in the post peak behavior, and you can also see the difference in the pre-peak region. In the pre-peak region, you can see for this low strength concrete, it's sorry. As the strength increases, the stiffness increases. So you can see increase in stiffness, increase in slope with these curves, and that eventually represents your elastic modulus also get increased with increasing strength.
బాగా హిట్ అయిపోయిందంట సూర్యది నిన్న రిలీజ్ అయింది చాలా బాగుంది బయోపిక్ చాలా బాగుంది నిన్న నైట్ ట్రైన్లో.
So as the strength increases, your elastic modulus will get increased and you will have a longer linear response and a sharper post peak, and you will have less post peak response when your strength increases. And this gives this restrained response when your member is subjected to compression and tension. So when you have uniaxial compression after certain load, you will also tend to have lateral tension that is induced. So you are applying axial stress here. So as shown in here, this figure, you will be applying axial compressive load, and this axial compressive load will induce lateral tension. So then your member will start strain in the lateral direction as well. So here this epsilon 1 that basically represents your axial strain, so change in dimension due to this axial compression force. So this strain response, basically the compressive strain is the axial strain induced due to the applied compressive load. Whereas this epsilon 3, so that represents the lateral deformation. So because of this axial deformation, so you know the Poisson ratio is that the member has a tendency to maintain its dimensional stability. So when you are applying the, when you try to compress the material, so to keep up the same value, the material has tendency to deform in the other direction, so that that can compensate this axial compression by deforming it in a lateral way. So the volume will be maintained for a particular specimen. So that's where the Poisson ratio comes into role. So when you apply this axial load, so the member tends to maintain the dimensional stability, so it deforms laterally. So you get lateral strain as well when you have the axial strain. So the ratio of the lateral strain to the axial strain is called Poisson ratio, right? When this material deforms significantly, you will start seeing reduction in the volume. So in that case, this central portion, that represents the volumetric strain. So that basically the relationship between volumetric strain is that one part of this axial strain is equal to 2 times your lateral strain. So you can see your volumetric strain will also increase with loading, but beyond a point, your material will get fail and your material will be collapsed and deformed. In that case, your volume of the material will be deteriorated. So there you can start looking at this reduction in the volumetric strain. So that basically represents the failure of your material. So beyond this line indicates this sigma A that basically represents axial stress. So in which, after which the transverse strain, that means the lateral strain increases considerably due to the Poisson's effect and your material will fail. Now let's look at the response under confinement. So confinement means how stiff your material is. Basically that depends on the strength of your concrete as well as the reinforcement that is there in the concrete. So for reinforced concrete, we provide steel, certain amount of steel in the form of longitudinal reinforcement as well as in the form of shear reinforcement called stirrups. So when you have such reinforcement present in your system, your concrete will be confined because these steel present that is there will give more resistance and that provides more confinement. And also when you have higher strength concrete, because of the high stiffness, your concrete will be confined. The point is when the confinement increases, the effective strength of the concrete increases because you will have a very stiff system to resist the load, so resistance will be increased significantly. So when your system, when your concrete is confined, your strength will be more. So the confinement can be in the form of increasing the compressive strength of your concrete, or in sometimes you can provide reinforcement to increase the confinement. Okay, so here this plot basically represents the increase in confinement and corresponding increase in the strength. So these values represents, this is a 0 when you do not, when you have no confinement, your response will be something like this, and when you increase the confinement of concrete, you are eventually increasing the strength, as well as the peak is also increasing and the post peak behavior is also increasing, because when you provide reinforcement, that has tendency to absorb more strain, and thus the ductility will be increased. And this effectiveness of confinement is lower for higher strength concrete. So you can see after certain so this is low strength concrete and this is high strength concrete. For high strength concrete, this effectiveness will be less. Why? Because the concrete itself will be very stiff. So in that case, if you try to provide more confinement, that will not be effective, because the stiffened concrete will tend to fail more in a more brittle manner. So in that case, even if you provide confinement, that will not be effective. That is a point here why the effectiveness of confinement is lower for high strength concrete. Here also you can see for high strength concrete, you can't see the post peak behavior, because the nature of high strength concrete is to fail in brittle manner. That is the reason here why confinement is not effective in high strength concrete. So basically, when you want to increase the strength and ductility of your member, so here you can mention this point. So when you want to increase the ductility will also get increased. So now let's look at the loading conditions. So when you do testing for concrete, we have different loading condition combinations. So whatever that I discussed so far is uniaxial compression. So that is the loading condition that we use to characterize the mechanical performance of concrete. So in uniaxial compression case, you will be applying the load in one direction. You can see here, so the load is applied from the top and bottom. So this indicates the uniaxial case, where the failure planes will be in aligned to its load path. And then we have this biaxial case, where compression will be applied in both directions, from top to bottom and then from sides. And here the failure pattern will look something like this in the other direction. And there are a combination of this compression and tension. So where you can see here in the axial direction, you are applying compression, and in the lateral direction, you are pulling your specimen. So you are applying tension. And biaxial tension is there. There you will be applying tension in both directions. And then the failure plane will look something like this in a horizontal plane. And the the final one is triaxial compression. So this is the case when you have your concrete in the submerged conditions. The hydrostatic pressure will be applied in all the direction of all the surfaces of your concrete. So from all the sides, the compressive force will be applied. So there will be a triaxial compression state when you have submerged conditions, right? Typically, this biaxial tension is not common when you use the concrete structure, because that may be induced indirectly by bending your member, but directly the biaxial tension is not the common case for concrete. But most often uniaxial compression loading case will be good enough to identify or to characterize the concrete. And this Mohr circle basically helps us to understand multi-axial stresses condition in your concrete. If you want to do test for different combinations, then this Mohr circle will be helpful to get an idea about the stress state level. Okay, so this theory is not directly applicable to concrete, but it is a convenient way of representing failure under multi-axial stresses. So when you know your stress thing, so you can plot the Mohr circle to identify the stress state and the principal stress axis. So you can see when you have a the right side you have tension and left side you have compression. So when you have simply uniaxial tension, your stress and strain will be less. And when you have, because the concrete is not good in compression, sorry, not good in tension, so less stress will be sufficient to fail your concrete. So that's why your stress level is very less when you have a simple uniaxial tension. And when this gets switched here, you have the combination of compression and tension. So the stress is slightly increased because the concrete can take more compressive stress. And when you have just compressive load, then the stress is significantly, like comparing to the simple uniaxial tension, simple uniaxial compression can take more stress because concrete is good in compression, so it can withstand compressive load better than the tension. And when you experience this triaxial compressive state, your stress will be significantly increased to withstand the loading condition, and the strain will also be more. And here you have this Mohr rupture envelope. So this basically represents as long as your stress is within this limit, you will it is under safe. So these are some theory that will help us to represent the failure under multi-axial stresses to simplify the assessment. And now, based on the stress-strain relationship, we can come up with some constitutive relationship between the stress and strain. So basically, that represents when your stress-strain behavior is linear up to I'll just draw it here. So you have your stress here, you have your strain. So you have your stress here, you have your strain here. So in this initial region, your behavior is going to be the linear. So approximately when you have 40% of your ultimate strength, then you will experience the linearity. So above this 40% of ultimate load, then your material will be behaving in non-linear fashion. Why? Because the non-linearity is mainly due to the heterogeneity of concrete. As I told, there are a lot of micro cracks present in the concrete matrix, and you have ITZ, that is the intertransition zone, where you have where you have cement and aggregate interface. So the failure will be mostly in the weak plane. So because of that, you will have non-linearity due to the heterogeneity of concrete, due to the presence of microcracks and the growth of microcracks with increasing load. Most often, the strain corresponding to the ultimate stress will be 0.003 for normal strength concrete, and this strain will be reduced for high strength concrete. High strength concrete will not experience such high deformation, and once the peak is reached, the member will break immediately in a brittle manner. For high strength, this may get reduced. The strain value will be reduced. So the concrete behavior will be similar in tension also, but the stress range will be less because concrete cannot take more tension load. It will easily fail when it is subjected to tension. So based on the post-peak behavior, we have different types of post-peak behavior. Why we are saying why it is important. So if your member is a brittle manner, so once the peak is reached, the member cannot take further load, so it will fail So the sudden failure will be known as brittle failure. So since they cannot take any stress further after reaching peak, that immediately fails. That means your stress, your member fails and the stress becomes zero. So once you basically the failure is kind of releasing the stress. So the member cannot take further load, so that releases the stress, and then that tries to keep it in a stable form. But depends on the nature of the material. If your material cannot take further load, then it breaks. So this is a good example. You can consider a chalk or glass. You break it, it can take certain load, and once the ultimate load has reached, the material will be broken suddenly. So that is the example of brittle failure. So your member will be deformed suddenly and it cannot take any further load. So you will see sudden drop in the loading or distress. So that failure is called brittle failure. If your member is a quasi-brittle material, so you will start looking at drop in stress after peak, and if the strain will keep on increasing. So the member has tendency to take load, but that load will be less than your peak load. So with increasing deformation, that represents that your material is carrying certain load. That's why you can start looking in you can observe drop in stress after peak. So the member is deforming, but the member cannot take load. That's why the stress is getting dropped after reaching the peak. So this is termed as strain softening. So your material is so soft, it cannot take further load after reaching peak. You will observe this kind of drop in stress after peak. So this represents strain softening behavior. If your member is elastoplastic material, so after reaching a peak, your member will deform at a constant stress level. So it is a case of plastic nature. So once the material has reached its limit, and you can deform, you can stretch the material at the same loading condition. So the load will not be increased, either it will not be increased nor it will not be reduced, but it will be at the same level, but the deformation will be increased in the case of elastic plastic condition, if your material is elastic plastic nature. Whereas if your material is a strain hardening nature, after reaching peak, the localized deformation will help you to resist further load. So that will the localization of defects will help you to increase the resistance, and that will help you to take further stress. So you can start observing this kind of behavior after this peak. The strain will increase, but the rate of increase in strain will be less comparing to the peak portion. But still, the strain will be increased with increasing strain condition. So the stress will be increased with increasing strain condition. So this is called strain hardening behavior. For this, steel is a very good example. You can observe strain hardening behavior in steel. This elastoplastic material, any material which is in plastic nature, that behaves in this way. And the strain softening is an example of concrete. And brittle nature, you can observe this in any like kind of glass or chalk material which can get break applied load. So this is just to summarize the stress strain behavior. So here you have your deformation, and when the load increases, stress is also increasing. So up to 30%, you have this minimal fine cracks at the interface. So minimal ITZ cracking. So the ITZ region, you will have fine bond cracks, right? And here in this region, when you have your loading condition from 30 to 70, there this fine crack starts growing slowly. So now this ITZ cracking becomes more severe in the range of stress from 30 to 70%. And with further increasing the stress, I can see the crack has all the ITZ has cracked, and you can see a lot of bond cracks at this region. And beyond the peak, you can see this region where the cracks are accumulated, and leads to a significant failure plane. So most often when the crack fails, when the concrete fails, your failure path will be through the cement paste. Okay, because in concrete matrix, your aggregate is the stronger material, so it is very difficult to break the aggregate. So the cement particles get crushed, and then that forms a weak plane, and your failure will be through the cement paste or the mortar. So if you see any deformed or failed concrete specimen, most often you can see the cement particles or the cement mortar that failed by crushing, and then that will lead to exposed concrete region. In some cases, as the strength of your concrete increases, especially when you have high strength concrete where the compressive strength is greater than 60 MPa. So in that range, almost your cement paste and concrete will have similar strength. In that case, you may end up seeing crack through concrete. So your aggregate. So your aggregate plane become almost your aggregate and your cement will be in a similar strength, and especially when your cement strength is greater than your aggregate strength, then you can see failure plying through aggregate. So there you can observe rupture of aggregates. So there the nature of failure will be brittle failure. So now obtaining or capturing the post-peak response of concrete is very important to characterize the nature of material. Because here you can see in this curve, until the peak point, you can't identify the nature of your material. All the regions were similar. For all the materials, you have similar. For all these four, you have similar or the same pre-peak region. So to identify the nature of material, either your material is brittle or your material is strain softening or your material is elastic plastic or your material is strain hardening. So to know these characteristics, you have to capture the post-peak behavior. Most often, the old test equipments, they don't capture the post-peak behavior. So why? Because those are based on load control method. So once the peak load is reached, the specimen will fail and you will fail to capture the post-peak response. So to obtain the post-peak response, you should have a test machine which can be tested using displacement control method. What is this displacement control method? I will explain the procedure in detail in the next slide. So in displacement method, you apply some displacement in a fixed condition. Okay, so when your test specimen is in the fixed condition, when you are applying a load displacement, that displacement will lead to deformation and that will induce stress. So you are applying load in terms of displacement. By commanding your specimen to deform this much, you are deforming your specimen by increasing the load. So small increments of displacement are given to the specimen and thus they decreasing the load beyond peak load, and then we can capture the peak load response. Typically, the strain failure will be around the range of 0.005 for normal strength concrete, and this will get reduced for high strength concrete. Most often, the post-peak behavior is a function of stiffness of your testing machine in relation to the stiffness of the test specimen that you are going to use, and then rate of strain. So basically, it depends on the stiffness of both test machine and then your sample or the specimen that you are going to test and the loading rate. With increasing strength of concrete, brittleness is also increasing, and this is shown by reduction in the strain at the failure. This is what I meant here. This 0.05 strain will be captured for normal strength concrete, and this strain will be reduced when you increase the strength of concrete. So for high performance concrete, the member will not deform or the strain will not be reached about 0.005 as in the case of normal strength concrete. So there, once the material reaches the peak, immediately you will observe the failure. So the strain will not be reached high, and most often the strain will be very less after post-peak behavior for high strength concrete. So here it represents the displacement control test method and the concept. So here you can see this. This indicates your concrete specimen, and you are applying load. Compressive load is applied. So here you first of all do this the displacement control test method. You need to have an actuator, and then the load cell to monitor the load, and you have the hydraulic power that basically gives the power to operate the testing, and you have servo valve controller. Okay. So from the hydraulic power, you give the you are sending a feedback signal to the servo valve, and then the actuator will give the displacement rate, and for the corresponding displacement, the load induced will be measured, and that feedback will be given to a controller, and that controller will send the feedback to the data acquisition. This data acquisition actually gives us the data in terms of load and the displacement. Okay, so with the help of data acquisition, we can obtain the load displacement behavior of the specimen. So you can see here, if you are, this shows the difference between load control and displacement control method. So if you use your load control method, you will be applying a load. You can see this red color arrow, you will be applying a load, and the displacement corresponding to that load will be recorded. And then you will be increasing the load, and then displacement corresponding to that load will be recorded. Further, you will increase the load, the displacement will be recorded, and further when you increase the load, the displacement will be recorded. But here in the ultimate load, because the specimen cannot take load because you have applied enough load that the material can take. So the failure will occur at that point, and further you cannot increase any more load because the material cannot take and it cannot capture its displacement. So when you use the load control method, your failure will be stopped at this point itself when the material reaches its peak. Whereas when you use the displacement control method, there you are asking your specimen to deform, and then you are recording the load which is required to cause the deformation. Again, you are increasing the displacement rate, and then the corresponding load will be recorded, and then increasing the displacement and the corresponding load will be recorded. Here the advantage is that, after peak, your material cannot take more load. Okay. So there, after peak, it becomes so easy for your specimen to deform, and then the specimen can take less load. So that is what captured here. So after peak, you will have a deformation, and then by the time your specimen reached its peak condition, so your specimen is kind of free to deform. So very less load is required for that particular deformation. So you can capture the drop in the post-peak region. Again, you will be deforming. For that particular deformation, you will require very less load. So the corresponding load will be captured. So with the further increase in displacement, reduction in load will be captured when you use the displacement control method. So the advantage of using displacement control method is you will capture the post-peak behavior. So capturing this post-peak behavior will helpful to understand the toughness nature of your material. What is toughness? Toughness is the amount of energy that the material can absorb before it fails. So that is what we call as toughness. So if your material or member has more toughness, that basically represents the material will deform a lot before it fails. So in that condition, it represents the ductility of your system. So if your toughness is more, ductility will be more. So for lower concrete, toughness will be higher comparing to the high strength concrete, where strength will be more, but the post-peak behavior will be less. The area under the curve basically represents the energy absorption, which is what we call as fracture toughness. So fracture is nothing but after the particular load, your concrete fails. So the sudden failure, the nature of failure is what we call as fracture. So that whole term is called fracture toughness. So the amount of energy that is required to fail is called fracture toughness, and it represents the ductility of your system. And here you can see the representation of toughness. So you have your stress strain behavior, and when you do your when you obtain your stress strain behavior, you can calculate the area under the curve. So the area under this curve basically represents your toughness. And this varies with different strength of concrete. As the strength increases, your peak region increases and these portions get reduced, and the post peak behavior will also get reduced. And this fracture toughness is very important for different applications. So when you do this under compressive stage and flexural tension and impact tension, the toughness has to be measured to check the ductility of the member. So how do we do the flexural toughness in laboratory? We basically obtain this flexural toughness by doing flexural loading. Flexural loading is nothing but you are applying load in the transverse direction to the specimen. So you have your concrete beam here. You are applying load perpendicular to your concrete beam. So that is what we call as flexural loading. So axial loading is you are applying loading along the axis of the member. So axis of the member, that is called axial loading. So flexural toughness is obtained by doing bending test, that is flexural testing. So you will apply load perpendicular to a concrete member. So this represents your loading case, load plateau. So you are applying 2-point loading. So most often we divide up, we tend to have such moment regions. So we split the span into 3. So you will have this L/3 span ratio conditions, and here you will have only pure moment. So when you have support regions, shear will be more. So to have a pure moment conditions, we are splitting into this L/3. And then you have LVDTs placed at the ends. LVDTs are basically placed to measure the deformation. So those are the displacement recorder. So when your beam is deforming, the deformation will be measured by this LVDT. So you are applying load and then corresponding deformation will be recorded. So this will help you to obtain the load displacement curve. When you have load displacement curve, you can calculate the stress strain response. So load by area, you will get stress, and change in deformation, you will get the strain. So you can plot the stress strain curve and you can obtain the curve like this, which represents which can help us to get the toughness of the material. And now we will look at tensile strength. So tensile strength is for concrete, it's very difficult to do direct tensile test, because when you have to apply tension loading, you have to grip the concrete member. So most often we will have cube specimens or cylindrical specimens. When you have to pull the concrete in this way to apply direct tension, you need to grip this portion. So you have to fabricate some special fixtures to grip your concrete. Most often the case will be very challenging and difficult to fabricate the grips for concrete to do uniaxial tension test. So that's why uniaxial tension test is not commonly used. We mostly use indirect tension test by applying compression and inducing tension indirectly. So here you can see it's a cylindrical specimen. Cylindrical specimen is kept in a uniaxial universal testing machine. So both compression, all the tests will be done use the help of UTM, universal testing machine, right? So when you have your specimen and when you apply the load, uniaxial loading, it has a tendency to induce lateral tension. So indirectly we are inducing tension by applying compressive load. So that is what we call as indirect tension test. It's basically based on Risalian splitting tension test method. And this is the relationship to get the tensile strength value. Since it is the indirect tension method, you will be using this relationship 2 times P by the circumference area, surface area of your specimen to get the tensile strength. Here is the relationship of the stress versus your maximum stress, that is your tensile strength. So compressive strength has a relationship with all the parameters of the concrete. So if you have, if you know the compressive strength of your concrete, you can calculate the elastic modulus of your concrete if you cannot do testing. So IS code has specified the empirical equation. By using that equation, you can calculate elastic modulus. Likewise, when you cannot do the tension test, you can, if you know the compressive strength of concrete, you can use this thumb rule. So typically, your tensile strength will be in the range of 8 to 12 times the, not times, 8 to 12 percentage of your compressive strength. So most often we will round it off as 10 percentage. So if you know your compressive strength is, if your FC is about 40 MPa, then you can empirically calculate your FT, that is your tensile stress. So that would be 4 MPa. So 10 percentage of your compressive strength. So if you cannot do the indirect tension test or direct tension test, if you know the compressive strength, then you can obtain your tensile strength of the concrete. So this plot basically represents the experimental test results that was done by various researchers. So those were collected and plotted together to come up with the relationship between tensile and compressive strength of the concrete. So based on this relationship, we found out that tensile strength would be about 8 to 12 percentage of your compressive strength. Similarly, we have relationship with the flexural strength also. For flexural strength, that basically represents the modulus of rupture. IS code has specified FCR, that is the modulus of rupture is 5700 point, sorry, 0.7 root FCK. Zero 0.75 root FCK. I'm not sure, is it 0.7 or 0.75? You can check in IS 456. So modulus of rupture relationship is given in IS 456. If you know the compressive strength of concrete, you can get the modulus of rupture. And another factor, another strength criteria that we look is that fatigue strength. Fatigue strength is nothing but if you are experiencing repeated cyclic loading. So cyclic loading in the sense you will be applying load and then load will be removed and then again you will be applying load, right? In the repeated cycle, the load will be applied. So load will be applied and then it dropped and then load will be applied and then it will be dropped. So this is the most common case when you have this bridge structure or when you have tunneling structure where you have this vehicle passing through. So depending on the number of cycles, you can classify the fatigue range, low cycle fatigue and high cycle fatigue and super high cycle fatigue. So in that case, the number of cycles you can see. So the low cycle fatigue is structure subjected to earthquake. High cycle fatigue is airport, pavements and bridges, and highway and railway bridges, and highway pavements and concrete rail to road types where you can see passage of vehicles. And then super high cyclic test is rapid transit structures and sea structures where the waves will hit and go on and off. And this basically represents the number of cycles. So when we design concrete for that particular applications, we look at this number of cycles and we design the strength like your concrete should withstand that many number of cycles without failing it. So the highest stress that a material can withstand for a given number of cycles without failure is called fatigue strength. So the fatigue is often represented, the fatigue life is often represented using the plot called SN curve. So SN curve means that gives the relationship between the stress level, that is the maximum stress, and that fatigue life number of cycles. So you should know this SMax, it's a ratio to your stress level to the static strength, maximum stress to your static strength. Okay. And this represents your mean fatigue strength, and 5% to your mean fatigue strength, and 95% to your mean fatigue strength. So if you are designing your member for this, so if your stress level is at this level, then your member should withstand the cycle of about this range. So if the cycle goes beyond this, then your member may fail. So here you can see with respect to time, the maximum and minimum stress that the member can take for a given particular cycle. So either if the stress exceeds this maximum limit, you will experience the failure. Else, if the stress exceeds the number of cycles, you will experience the failure. So that's why most often it is represented using this SN curve. So the fatigue strength is the highest stress that the material can withstand for a particular number of cycles without breaking it. So if your number of cycle is 10 to the power of 5, and if you are designing your member for this particular 0.8, then this will be your fatigue life. So if the stress increases beyond this, then your member may fail, or if the number of cycle increases, then your member may fail. Another important strength is that steel concrete bond. So this is the main thing that governs the composite action when you have steel and concrete system. Okay, so when you embed steel in the concrete system, you should have an idea how well the bonding would be between the steel and concrete. To check that, you should know the steel concrete bond strength. Okay, so for identifying this, determining the steel concrete bond, most often we apply tension load in one direction to the steel. So basically we are trying to pull the steel out of this concrete. So that will give us an idea how well this steel is attached to the concrete. So as we pull, after particular loading condition, this bonding at this region will get affected at the interface, and this strand or steel that will start slipping, and this deformation will slowly affected from this region to the end of the rebar. So once the strand starts slipping, that basically represents your bond is failed. The bond failure of steel reinforcing bar occurs due to crushing and cracking of the surrounding concrete. So when you pull this out, the stress will be induced at the interface, and the strand or steel will get detached from the concrete. So in that case, the interface get damaged. So their bond cracks will occur. When the stress is so high, and if the concrete cannot crack, the concrete will start crushing. So most often the failure will be in the nature of crushing and cracking. And some cases the cover will be cracked, and you can see this kind of split crack formation in the cover. So splitting cracks will occur in the cover. So this is the example of split crack when you apply a tension in one, apply a tension to pull the steel from the strand. And here is the case, you apply the tension and the compression will be induced in the concrete, and here this kind of develops a wedging action. So your steel, when you apply this tension, the reduction in diameter will be occurred due to this axial load. And whereas the rebar that is there in the inside will be in its original dimension, and that will kind of form this wedging action. So once the wedging action is so significant and the load is also increasing, that will result your concrete to crack. And depending on the ribbing, some ribbed bars will be used in the concrete. So depending on the ribbed bars, your crack will also, inclined cracks will be developed due to the presence of ribs on the steel surface. So these are some mechanical characterization of your hardened concrete in terms of evaluating its strength and ductility performance. So generally, when you characterize any material, first, especially the concrete material, first you will look at the fresh properties. So where for identifying the fresh properties, you need to check the workability property, the use of slump cone, VB consistency, and inverted slump cone test method. So inverted slump cone is not in the scope of this course. And the second property is shrinkage cracking properties, because when you use this cement So that has tendency to change when it is exposed to environmental condition, volumetric change. So in that case, you need to know how well the shrinkage properties are during the initial stage, early age, and long-term performance. And the initial age means you will be looking at the plastic shrinkage. So I will cover in detail about this shrinkage mechanism in the coming slides, where we talk about durability. So there, if you are in case of long term, there you have the classification of free shrinkage and restrained shrinkage, and you will have some residual stresses. If you have your free shrinkage, then your member is not restrained to crack. In that case, your member is free to move, and stress will not be induced in the member, and crack will not be developed if you have free shrinkage. Whereas if you have restrained shrinkage, there will be restriction to your movement, your concrete movement, and if there are any restriction to your concrete movement, that will induce stress in the concrete, and that will lead to cracking, right? Here, now we looked at this hardened property of concretes, the mechanical property. So where we discussed about the strength, toughness, and impact resistance. Impact resistance we did not cover in detail, because impact resistance is kind of like how your material is going to resist the sudden loading. Okay, so that again depends on your sustained behavior of the member. Whereas your load rate will be sudden, so in that case, the failure will be in a brittle manner, and the strain deformation will not be more. Ductility will be very less if you experience impact loading condition. And then durability performance we will discuss in the next lecture. So how the permeability or the voids and pores that is there in the concrete will be harmful to the concrete by allowing other foreign elements to enter into it, and that will affect the strength as well as ductility property of your concrete. Right? So those things we will cover in the durability aspect. Fine. With that, the hardened property of concrete is over. So we have only one topic left out, that is durability of concrete. After that, the type of concrete will be given as assignment. So you can work on the different types of concrete, basically to understand the properties that we discussed during the lectures regarding the fresh and hardened properties of concrete. Basically, when you change the type of concrete, you will be using different types of cement and different types of aggregates to obtain the required performance. So that can be lightweight. If you are looking at lightweight concrete, you will be using different types of aggregates, which will help you to reduce the weight of concrete. If you are looking for high performance concrete, you'll be using more SCMs in the concrete structures to get the both strength and the durability performances. Okay, fine. Let's meet tomorrow at 9:30. Thank you.